Good evening, everyone, and welcome to another edition of Virtual Starry Skies. My name is Joe Aiken, and I'm the director of the Haute Tongue Visualization Lab and Planetarium at Colgate University. So I'd like to welcome everybody to this great evening and happy Memorial Day weekend. So tonight, we are going to actually talk about planets orbiting other stars. We actually call these exoplanets. Now, of course, we always like to start off just kind of showing what's up in the nighttime sky. I mean, I'm actually going to do this kind of brief because then we're going to head off to other solar systems and other star systems. So, first off, what we're going to do is actually just fade this down. And if anybody went outside over the last couple evenings and looked very low in the west, you would have seen something very interesting. In fact, let's take a look. So this is what your sky would look like looking west tonight, roughly around 9 o'clock or so. So about an hour after sunset. And if you look very low in the sky, right above the horizon, you might have seen two fairly bright objects. One really, really bright, of course, and then one right below it. Tonight, they've switched places just a bit. And of course, I'm talking about these two objects right here. And if you look, you'll see these are actually not stars, or in fact planets. And one of them, of course, is the closest planet to the Earth. And if you notice when we zoom it up, this is, of course, the planet Venus. Venus is a very thin crescent. If you've been watching over the last several weeks, watching some of our shows, you would have learned that Venus is actually about to disappear below the horizon and pass in front of the sun in what we call a conjunction with the Earth. This is actually a very, very thin. It's a little bit closer to the Earth, so it's extremely bright right now. It's a great time to see Venus. Right next to it is a planet that we don't get to see very much because it's always right next to the sun. And that is, of course, the planet Mercury. And we zoomed it up. If you notice, both Venus and Mercury go through phases. That's something special about planets that are between us and the sun. We can actually watch them go through their phases. So you'll be able to see Mercury over the next several nights, right next to Venus tonight. And then over the next couple of nights, it's going to slowly get away from Venus. And there's another visitor actually going to be joining these two over the next couple of days. So let's go and scale Mercury back down. And I just want to show, let's move forward a couple of nights just to see what happens. So if we go out the same time, let's say tomorrow night, Venus gets a little bit lower in the west, Mercury gets a little bit higher in the west. Then watch what happens on Sunday. We get another visitor, and you can barely see it there, but you might notice a very thin crescent moon. And that's, of course, our waxing crescent moon. That's going to be out from under the sun, coming up on the horizon, right next to Mercury. So again, a very nice picturesque opportunity on Sunday if it's clear. And then over the next several nights, of course, the moon's going to get further away from Mercury, but Mercury will be doing a little dance there in the west over the next month. Now, watch next month, and we're not going to talk about this tonight. We'll talk about that next week. But Venus will actually be joining three other planets in the morning sky in the next couple of weeks or so, about 3 weeks from now. So late June, watch for Venus to join Mars, Jupiter, and Saturn in the morning sky. Okay, so that's enough about the planets. We'll go back to tonight here. We are actually going to be looking at planets orbiting other stars, not just our own solar system. So, let me put up some markers here. Here you can find planets orbiting other stars. We have a lot. And over the last, most of these discoveries have happened in the last decade. We have found confirmed planets orbiting other stars, over 4,000 of them. These are just some of the markers. The most recent discoveries have come with the deployment of two spacecraft, one called Kepler and the other one called TESS. And we will talk about each of those in just a bit. Let me go and turn these markers off, and I'm going to put up some little, just a few statistics here. So like you said, there are over 4,000 confirmed planets. Most of these planets are gas giant planets or Neptune-like, so about 1,300 gas giant, nearly 1,400 Neptune. These are a little bit smaller than like Jupiter, but we have discovered nearly 1,300 what we call super Earths. These are Earth size or bigger, and then a handful of smaller objects. Of these, there are different methods of actually finding these planets. We have transit method, radio velocity, microlensing, we have direct imaging, and then about 1% others. We're going to talk about each of those and what tools astronomers use to actually find these planets orbiting other stars. We actually call them planet hunters. All right, so let's talk a little bit about these methods of detection. Because in the early 20th century, up until about the mid 90s, we found maybe a handful of planets orbiting other stars. It took astronomers newer technology in order to see these planets and other types of method. So let's talk about each one. So what we're going to do is I'm going to put up kind of a demo system, if you will. We're going to have a star, we're going to have a planet. All right, so let's start off with that. Just give me 1 second here. What you're going to see is this scene's going to fade out, and we're going to put up a star with we'll start with a Jupiter-sized planet. So here you can see Jupiter, or a Jupiter-type planet orbiting its host star. Now, of course, these stars are scattered throughout the galaxy, and there are different viewpoints from the Earth looking at these objects. Let's first talk about a method called radio velocity. And what that means, it makes up about 20% of the discoveries that we have made have been using this technique. And I'm just going to put up a graph here, and then I'll talk about it. So what you're going to see, you see that planet orbiting around. Notice that the star itself is moving back and forth. We actually call that a wobble. The star wobbles because of the planet orbiting on it. Both objects, even though the star is much more massive and much larger than its planet, they share a common center of gravity, which means now that common center of gravity might be within the host star itself, but it's off just a bit to actually make that star wobble. Now, astronomers actually use what we call spectroscopy, one to look at the chemical makeup of the star, because every element actually shines in a certain part of the spectrum. This is actually looking at, let's say, visible light. You see the colors there from purple to red. You see the graph to left. This is actually what we call a light curve. In this case, it's actually a spectroscopy curve, but we won't get into the physics of that. So as the planet orbits around, it makes that star wobble back and forth. Now that star wobbling will move towards us and away from us. When it moves towards us, we can see the shift in the spectrum shift towards the blue end. When it moves away from us, that spectrum shifts to the red end. Now, we are exaggerating the effect here just for proof of concept. In reality, this is a fraction of a fraction of a percent. So these are tiny changes, but astronomers can use that to determine what size or what mass of object could be orbiting a star if you see that star wobbling back and forth. Now, early detections, the best we could do is 5 times the size of Jupiter or larger. As methods got better and we got better at detecting or seeing the curves, we were able to get smaller and smaller objects or observe smaller and smaller objects. And just kind of show you what, like, you can see that little spectrum shift. If we make the planet small, you'll see it's a smaller shift. All right. Well, it's a smaller object, but massive, more massive. If we make the planet lower in mass, you'll see a smaller shift in the spectrum. Okay. Now, another method astronomers use is kind of a newer method, in quotes. We actually use what we call the transit method. And it wasn't really until the spacecraft called Kepler, which was launched, to be able to actually use this method to determine planets. And the idea is, and let me take out the radial velocity. So the idea is if you take thousands of pictures of a star field and you can detect the dimming of light by a fraction of a percent in front of these stars, you know that something probably passed in front of it. So let me put up another graph. So if you measure the star's brightness or its luminosity over time, it should be pretty static. Now, sometimes you have stars that might be variable, have something weird going on inside. It might be losing its energy, so it'll change its brightness, and with a common fluctuation. When something passes in front of it, it will dim its light by a fraction of a fraction of a percent. If you look at the graph as it goes along here, you'll see that dip as the planet passes in front. We can measure that dip, also the dip in luminosity, to determine the mass of the planet. We can take the spectrum using the radial velocity to determine maybe like basic elements that that planet might be made up of by taking out what the star is made up of. Now, this only works if the planet and the star's orbit, or the planet's orbiting around a star, is in direct line of sight of the Earth in order to see it, or in this case, of the Kepler spacecraft. I'm just going to change the rotation of the orbit just a bit, just kind of prove my point. Watch what happens to the dip if we change our viewpoint and we make the Earth at 45-degree tilt, meaning that the planet will not pass in front of a star from our vantage point. You notice there is no dip, which means the transit method gets thrown out the window. So you kind of have to go back to measuring the star's wobble to determine if there is a planet orbiting it. If we go back to, let's say, perfectly edge on, and we put the planet in motion, you'll see a nice dip. So Kepler actually took thousands of images in one part of the sky over several years and was able to detect many, many planets. And we'll come back to that. Okay. There's another method that's just now starting to become more popular, I should say, but it's still kind of a different way of actually detecting planets. One of them is called gravitational lensing, and it makes up about 2% of the current planets that we discovered. Roughly around 80 or 90 or so planets discovered using this method. And what this means, this is a little complicated, it's kind of crazy. When the Hubble Space Telescope first looked at massive objects like clusters of galaxies, in one of the images, we noticed that there was part of the image from behind a cluster of galaxy appearing in different parts of the image. And it turns out Einstein over 100 years ago predicted this. He said usually massive objects should bend background starlight. That's a very simple way of saying it. And in turn, that's exactly what happens. So if we have a faraway star that we're looking at, and let's say another star in this little planet comes passing by in front of that star, we should see, due to the star itself and the planet creating a gravity well, it should bend the background starlight. So we have now a method of detecting this. And then we know that based on the signature, there should be something there. So let me put up a little graph. This is, again, brightness over time. And let's go and put a lensing event. let's put this in motion. So there you have that star. And actually, let's do this again here. So here comes a star with a planet passing in front of that background star, and you get this graph. You'll see the big kind of bell at the top there. That's the star. The little blip to the side is the planet. So if you have a bunch of little blips, there might be multiple objects passing in front. Again, this is kind of a newer way of detecting planets from ground-based observatories. And then right now it's making up about 2%. Okay. So it just kind of proved my point again. Looking at an event without a planet, here's what this looks like. You don't get the little blip. So if it's just a star or one object passing in front, you get a nice change in brightness over time. So what you're looking at is basically the dimming or the changing of light behind that star over time. It doesn't have that extra signature. Okay. There's actually a couple other methods that we can use. You can use less than 1% are using timing methods, and if there's a planet orbiting a pulsar, looking at the change of that pulsar over time. We're not going to talk too much about those. They make up a very small percentage, less than 1%. But there has been about 1%, roughly around 50 or 49 actually, planets being discovered by direct imaging. And what that means, we actually can physically see the planet itself. The first one, and let me bring this up, this image right here. This is a real image, kind of composited together. The big blue thing is actually its host star. The red blob down and to the left is actually a planet, and it happens to be a Jupiter-sized planet, actually about 5 times the mass of Jupiter. This was discovered in 2004 using the Very Large Telescope array, or Very Large Telescope, I should say. This was actually the very first exoplanet directly imaged, and it was well before kind of our current technology. The planet itself is about twice the distance as Neptune is from our sun. So you're looking at about 6 billion miles from its host star. One of the reasons why we could actually photograph this in 2004 using that technology is because the host star is what we call a brown dwarf. Think of Jupiter, but much more massive. Not quite as big as our sun, but much bigger than Jupiter. It's kind of a dud star, if you will. If Jupiter was on its own, we'd probably call it a brown dwarf. So think of it like a gassy planet that's not quite hot enough really to form a star, but it's by itself, so it's kind of a star. It never had enough energy, enough gas, hydrogen gas to actually start fusing enough to get into helium. So it's kind of this kind of like a dud star. So the Jupiter-sized planets, actually, we were able to directly image this. Another one came several years later, and this is over a 7-year period. So I'm just going to play this little movie here. This system, you can see 4 little dots orbiting its host star. Again, direct imaging. This was taken by using the Keck telescope over a period of about 7 years or so. So you can see the clock down the bottom left. This method involves masking out the star glow itself. Because if you may ever seen a star through a telescope or a pair of binoculars, especially if you take an image of a star, the star kind of outshines everything else in the image. So astronomers can use like a little disc, if you will, to block out the starlight to try to directly image these planets. Now, these planets are very far away from their star, roughly ranging from the periods that these massive planets take from 40 years to about 400 years. So you're looking at anywhere from probably about the orbit of, oh, I don't know, between Saturn and Uranus, all the way up to like Pluto in scale of our own solar system. So these objects are massive objects, or Jupiter size or larger. These are what we call super Jupiter size, maybe 5 to 10 times the size of Jupiter. So these are massive planets really far away from the star, which was the reason why we were able to actually image these. Now, sometimes you get a false lead in the instance of this image right here. Now, if you look at this image, this is actually a star called Fomalhaut. And if you block out the starlight, we are actually able to detect a ring. That ring of material is usually where you probably would find debris left over from the forming star, almost like an asteroid belt or a Kuiper belt. This is a little bit more dense of material. But inside this ring, we did detect this kind of blob, if you look at the image on the right, starting in 2004, and we took an image over several years. But you notice by 2014, it kind of went a little fizzling out, almost disappeared. So it turns out, we think, we're not 100% sure, but we think this is actually a cloud of dust that was created by the collision of objects. So imagine a couple asteroids a few hundred miles across colliding into each other and spewing out a whole bunch of debris and icy dust. And so it would glow for a bit and then fizzle out over time. And we think that's exactly what this blob is. Additionally, when we first took this image back in 2008, when we kind of looking back at some of these images, we thought that, hey, this could be a planet. It turns out it's probably not. It's probably just some debris that collided with each other. So comes along, we have to find some more planets, right? So astronomers back in March of 2009 launched the Kepler spacecraft. Now, Kepler looks something like this. I'm just going to bring up a 3D model of the spacecraft itself. This is actually one of the space telescopes. And let me rotate it around here. Let's see if I can do this here. And let me just kind of move us around so we can put some light on it. Now, this is about the size of a large bus. And so it's actually kind of a big telescope that we launched. Again, it was launched back in 2008. 2009, sorry. We got our first image about a year later, our first confirmed, I should say, not image, our first confirmed exoplanet. And it used that transit method to discover many, many planets. And what's cool about it, it actually looked at one region of the sky. Let's see if I can get this to load. So if you kind of look, I don't know if you can see my mouse coming in here, but this object right here is a star called Deneb, and it's actually part of the Summer Triangle. And if we zoom up just to the right in the constellation of Cygnus, what I'm looking at, what you're looking at is actually all the region of space that Kepler was first looking at. And it was taking, again, thousands of images in this one region of the sky. And let's kind of rotate around so you can see it here. There you go. So right over here. So with Kepler, it was actually to detect over 3,000 planets in this region, with over about 5,000 candidates that are still yet to be confirmed, because it takes a while. Once we get a candidate, we have to verify using other methods to make sure the mass and determine the planet itself. But here's the footprint that Kepler took. Something happened, though, several years later into its mission. It actually lost a couple of its gyroscopes, and the telescope tipped over. and But it wasn't the end of its mission. For the last couple of years, it lasted until about 2018 when we finally turned it off. So it lasted quite a while. It actually just kind of stayed in one axis along the equator of the Earth, and we were actually able to detect even more planets. So it wasn't the end of its mission by far. All right, so let me turn this one off. Now, fast forward to 2018. Let me turn off this. We launch a new telescope called TESS. That's TESS. Launched 2018. Since 2018, so in the last 2 years, we have discovered over 1,800 candidates. 47 of those planets have already been confirmed. And let me show you what this spacecraft looks like. So we're just going to fade this scene down. We're going to put ourselves in orbit around the Earth. And let's get a little bit closer there. So here's the spacecraft itself. It looks quite a bit different from Kepler. It's basically using several wide field of view cameras to take mini snapshots of the sky. And I'm going to try to load the region of the sky that it's looking at. So it might be a little kind of crazy. First thing I'm going to do is actually put up its first image. Let's see if we can get this to work properly. And it's basically looking towards the southern hemisphere. So as this loads up, we kind of rotate around here. So in 2018, we got its first light. These are super high resolution kind of field of view. Each tile was from a different camera. And then, of course, this is several days of data taking. And then they all get mosaic together to form kind of one image. And again, this is looking towards the southern hemisphere for the vantage point of the Earth. This is actually in orbit around the Earth right now, but you can see the large and small Magellanic Clouds, a few other objects. But with this, so as it's taking these images, astronomers will have to go through, and as more and more planets are being discovered, using, again, very similar to Kepler, using that transit method. But it can also look for other things too. You can actually detect like asteroids. It can detect possible black hole gravitational interactions. It can look at supernova observations, you name it. But let me turn off this image. And I'm going to try to load up a couple of sectors here. So eventually, this is going to be the map that TESS will be looking at. And let me see if I can zoom out so we can see it. And I'll just kind of rotate around here. So the idea is throughout its life, be able to capture pretty much the entire southern hemisphere sky and to look for these planets. So by the end of its mission, we should be finding tens to hundreds to millions of planets. At least that's the idea. Okay, so let me turn off that. So let's take a look at some of the planets that were discovered over the last several decades. So a couple years ago, NASA thought it'd be fun to make up some travel posters. So we're gonna start off with some of these travel posters and go to the planets that they're talking about, almost like the old 50s style travel. They made some up for the exoplanets, even for our own planets in our own solar system. Okay, so give me 1 second here. So one of the first planets discovered was around in the constellation of Pegasus. The star name is 51 Pegasi. And whenever we discover planets, we put the star name and then we put a letter after it designating which planet is in sequence of the orbit. So sometimes we find systems with more than one planet and we designate them with letters B through whatever. So 51 Pegasi was, again, one of the first exoplanets we discovered. It's around a star very similar to our sun. The first planet was, again, about half the size of Jupiter, but it's very close to its star. It only takes about 4 days to orbit its star, so it's very, very close. Less than the orbit of Mercury. And this was actually first discovered, well, at least it was announced in 1995, first discovered in 1994. So let's go visit it real quick. All right. So we're going to be flying around, popping around. So I hope you guys don't get too dizzy. And I'm going to be watching on time because I'm already kind of going long. So here we go. We'll go quick. So let's start off by going to 51 Pegasi here. And again, it's in the constellation of Pegasus. All right, so here we go. So you'll see it pop up here. And there is its host star. You can see the little planet to the left. I'm going to make it stop spinning here just so it's not so nerve-wracking. So there you can see that bright star, very similar to our sun. This planet was discovered using the radial velocity. Again, it's roughly about half the mass of Jupiter, but it's actually a little bit bigger than Jupiter itself as far as radius, but the mass is actually about half. So it's probably made up of even lighter elements than Jupiter is. And if we want to just take a look at what the planet might look like, remember, we have not had any images of the planet's surface or atmospheres on any of these. This is all fictitious, artistic drawings that we actually are putting in, or models. So these are not real images of these planets. I just want to reiterate that because the media likes to show all these pretty pictures of these exoplanets. We don't know what these guys look like. We can get a hunch by detecting elements in the atmospheres. We can look at the mass, but we really do not know what they look like. So here is kind of a fictitious version, if you will, kind of these gas giant planet. All right. But let's move on to our next destination. Like I said, we're going to be kind of go through these a little quick. So I got to speed up here. So let me put up our next poster. This is the planet named 55 Cancri E. This is around a star called 55 Cancri. What's cool about 55 Cancri, it is very close, like even closer than this planet that we're 51 Pegasi. It's even closer to its host star. So let's take a trip. And we'll turn this one off. Okay. And let's take a trip over to star dubbed Copernicus. And this is in the constellation of Cancer. So there you can see the star. Now, what's cool about 55 Cancri is it has several planets. It's not just one planet that we discovered orbiting around it. But the planet that we actually want to focus on is that one that's very close to its star. And it turns out that this planet is what we call a super Earth. Now, it takes less than 1 day to orbit around its star. So let's fly to it real quick. All right. Now, this star itself, 55 Cancri, is actually fairly close to our sun. It's only about 41 light years away. If you ever seen Star Wars, which I'm sure many of you have, you might recognize this planet as similar to that of Mustafar, where kind of Darth Vader, I guess, lives now, or pre-original movies. So imagine a planet that's very close to a star, molten hot on one side. If it's tidally locked, it means the other side is probably not molten. It might be almost frozen solid. Hence, Mercury, the day side of Mercury hits about 800 degrees, the night side minus 300. For 55 Cancri, though, it is extremely close to the planet, or its host star, so I'm sure it's pretty much boiling away, if you will. So there you go. Not a nice place to visit at all. But there are indeed 5 planets in this system. All right, let's take a look at our next one. This is actually another what we call super Earth. These are a little bit bigger than the Earth itself. They're rocky in nature. They're not gas giants. So let's take a look here. Here's our next poster. Experienced gravity of wonderful star name HD 40307, the planet designated the G planet of this system. So to get there, we are going to have to fly away. So we will scale or take this off. And let's head over to the star. Okay, so this star itself is a little bit smaller than our sun. It's about 3/4, roughly, the mass of our sun. It does have several planets orbiting in it. It actually has 6. But we're going to go fly to the one that we were talking about. Roughly, this super Earth is actually a little bit smaller than the planet Jupiter, but rocky in nature. So let's head over to there. This is one of the first, what we call super Earths ever discovered. And actually, I think I clicked on the wrong one. Let's head back over. This super Earth orbits its star in about 4 days. So here it is coming up. Let's zoom into it just a bit. Again, this is kind of a fictitious texture map that we put on. So it's very close to its star, not as close as the previous ones that we looked at. Again, roughly about 4 days or so. It's well within the orbits of Mercury. Remember, Mercury takes about 88 days to orbit our star. This is much closer than Mercury would be around this star. But again, very strange world indeed. So let's keep going. Now, this next planet, we're going to be looking at some of the planets that Kepler actually discovered. This one in particular was actually discovered in 2009. So this was not discovered by Kepler. It was actually using other methods like the radial velocity method to discover this one as well. This next one is actually using that transit method. And this is called Kepler 186f. And it's around an M-dwarf star. So imagine a star roughly 10 times less than the size of our sun, or mass of our sun, red, basically having much heavier elements, a lot of helium embedded in its core, diffusing, and it would be very kind of low energy. Which means, so the whole point of finding exoplanets is to look for planets that might sustain life. That's kind of the big question: is there other life out there? So astronomers think that in order to have life, you should have some sort of maybe liquid water. At least for the case of the Earth, we need pretty much water to have life. At least we think. That could be proven wrong, but or maybe we never know. But the zone that we call is that Goldilocks zone, where a planet's not too hot, not too cold. So it's warm enough to have liquid water, but not too warm where the water would boil away, or an atmosphere would boil away. And it's not too cold where the atmosphere would be frozen on the surface. So we call that the Goldilocks zone. So it turns out in our solar system, that can be anywhere from about Venus to Mars. Now, depending on the size of the star, that habitable zone can change. So let's head to this planet. Kepler 186f. It's also what we call a super Earth, discovered in 2014. And let me set this up and we'll go flying there next. Now, this system actually has five planets orbiting in it. This 186F, so there's the star itself. Let's zoom out just a bit. It's very much Earth-like. It's still very close to its star, but not as close as the ones that we've been watching or visiting. It's a little less than half an AU, which is about half the distance between the Earth and our sun. This planet to its star is about half that distance, which might make it within the habitable zone. And so we think anyway. So if you want, we'll take a look at the orbit here. And let's zoom out and we'll go flying to it. So those are the other planets. This is the furthest one out in this system. And so we think it actually has a nice stable orbit. It's roughly about similar mass of the Earth, actually almost double mass of the Earth. Its radius, though, is about the same size as the Earth, so we know it's probably rocky in nature. It takes roughly 129 days to orbit its star, so it's a little bit, again, about half that of Earth. If we fly to the planet itself, just kind of see what the surface looks like. Let's take a look at that. And again, this is kind of a fictitious surface, but it may have seasons, much like the Earth. It may have, looks like we might be getting into a little ice age here, so it might be further away because, again, the star is what we call an dwarf star, so it is lower in energy, so the further away you are, it's not going to have as much heat like our star. All right, so let's go to the next system. We're going to skip over a whole bunch of discoveries that have happened in this time, and we're going to fast forward to just a couple years ago. A system that has the most Earth-like planets that we discovered to date. And this is, of course, the planet system called TRAPPIST. TRAPPIST-1, actually. And this is our last poster that we're going to show from NASA. I just really like this one, though. So here we have voted best habitable zone vacation, because there are actually 3 planets in what we call within the habitable zone. And it's actually fairly close to us. This is only about roughly, I just lost how far away it is. It's actually within 12 parsecs, you can see in that poster. So roughly within 40 light years or so. It's actually about 39 light years away. So let's fly to that system and take a look at these crazy planets that we might find. Again, many of the planets are rocky in nature. So let's fly to the system. All right, there we go. It's kind of an orangey star, if you will, a little bit older than our sun. But there you can see all the little dots on either side. Those are all of its planets. 7 altogether. Roughly the planets E, F, and G, and let me put up those orbits here, are within this habitable zone. So these planets right here are well within the habitable zone, which means liquid water could exist. We have no idea what these atmospheres are or what is on the surface. But let's take a visit at 1. We're going to go to E, and let me turn off these other orbits here. So if it's in the habitable zone, it should, if there is water on the surface, it should be in the form of liquid, which means that, of course, if there's an atmosphere and it can hold water, there's a lot of factors there. But this is what it might look like, again, fictitious. But this planet in particular, most of them are actually roughly the same size as Earth. Some are a little bit bigger, some are a little bit smaller. In fact, all the planets in this system are roughly the same size as our Earth, which made the system very interesting and different from all the other systems that we've been discovering. This particular one roughly takes 6 days to complete one orbit. I'm going to put up our solar system. So let me zoom out of this planet a little bit. And we're going to put up the orbits of our solar system here, just to kind of show you in comparison. And in order to do this, I need to actually fly to the star itself. And we're going to put up some of these orbits again. Let me just do some of the ones that are in that habitable zone. And you're going to notice something kind of weird. The orbits are actually tilted to that of our solar system, but it will show the scale. So let me zoom out. It'll make sense once I zoom out more here. Okay, so that first circle there that says Mercury, that is the orbit of Mercury. All the planets in this system are very close to their star. The farthest one out roughly takes 18 days for that planet to orbit the star. So imagine having your birthday every 18 days, and that's the one that's furthest away. So you'd have a lot of birthdays. We'd be very, very old in this system. The closest planet, which is more like Venus, it's probably very, very warm. It takes roughly a day and a half to go around its star, around the star TRAPPIST-1. But anyway, very cool system. This TRAPPIST system. Okay, so let's go a little bit closer to home. And I'm just going to point out a couple more, and then we'll be finished for tonight. So the next system, I don't have a post for it, unfortunately, but this is actually, we're going to go really close to home. In fact, the closest star to our home besides the sun. And yes, we have found planets orbiting around this object. It's an M-dwarf star, part of a triple star system called Proxima Centauri. And it's part of the Alpha Centauri triple star system. Proxima is an M-dwarf star that orbits far away. So let's head over there. And we have discovered a planet. It is Earth-like, roughly about the same size of Earth. Just a little bit more massive. But again, Proxima Centauri is an M-dwarf. So in order for a planet to be habitable, in which we think this is actually in the habitable zone, it can be much closer to its star. In fact, this planet takes roughly 11 days to orbit Proxima Centauri. And right now we dub this Proxima Centauri B. Discovered in 2016. This is actually, we used the radial velocity to discover this. So since it's so close, you might think, wow, if it's a closest star, we might be able to get there in our lifetime. Well, okay, if we send our fastest spacecraft, or maybe not quite our fastest, let's send Voyager. It would take 75,000 years to get there with our current technology. And Voyager's just now at the far reaches of our own solar system gravitational pull. Proxima Centauri is roughly about 4 light years away. Remember, 1 light year is about 6 trillion miles. So 4 light year, roughly 30 trillion miles away from us. With our fastest spacecraft, 75,000 years. It took light 4 years to reach us. So again, we're not getting there anytime soon. But hopefully, you never know what happens with technology. But the laws of physics says we cannot travel faster than light. So our fastest speed, even if we could travel the fast speed of light, it would take us about 4 years to travel to this planet. Again, traveling at the speed of light. But I doubt this planet, it's around kind of this M-dwarf star. Doesn't really have a lot of energy like our sun, so who knows how stable this planet would be. I just want to point out a couple more, just because for fun. This next system is called Teegarden, and we've actually discovered 2 Earth-like planets around this star. So let's travel. It's a little bit further away than Proxima Centauri. It's kind of it's still close by, within 13 light years. It's also a red dwarf star, just like Proxima. And by the way, red dwarfs make up most. Sorry, we got a little close there. The red dwarf star makes up most of the stars in our galaxy, well, at least in our part of the galaxy. So there you can see the 2 planets. They are both within what we call that habitable zone. But again, they're fairly close to their star. Roughly the first planet there, if we travel to it, takes roughly 5 days to orbit its star. The next planet out takes roughly 11 and a half or so. They're both roughly the same size as Earth, at least in mass, roughly about Right, actually just a little bit bigger than the Earth, maybe a little bit more massive. But here's what this planet might look like. It's definitely rocky in nature. We put a little Mars texture on it just to show something different. Again, it would be very red with this red dwarf star. And so your sky wouldn't be as bright as on the Earth. Yeah, kind of cool. Now, real quick, let me check the time here. We are hitting roughly around 45 minutes, so let me move on. I got just one more to show you. We'll end with this object called LHS 1140. This is actually one of these super Earths. It's roughly 50 light years away from us. What I like about this one, we found it's a star that's much smaller than our sun, but the planet is about twice that of Earth. It's about seven times heavier than the Earth. This is one of the planets discovered, and this was discovered in 2017. So let's head over there, and we think that this planet is actually within the habitable zone, and it's what we call a big super Earth, because again, it's 7 times the mass, so there are heavy elements, and it's twice the radius, but 7 times the mass, so it's very, very dense. So let's head over to that planet real quick to see what it might look like. So there are planets stranger than we can ever imagine that we're discovering. Of course, we don't know what they look like. We can only use our imagination to find these. So let's take a look here. There is a great website that you can go to find some of these things. It's called Exoplanets. And let me just get the actual address. Exoplanets.nasa.gov. There's a really cool, I'm going to show you a little applet here where you can actually go and look at some of these planets for yourselves. So I'm going to see if I can do this here. I got to do a new share. So bear with me here as I get it set up. So hopefully you guys can see that, at least on the Zoom call, and I'm going to change it over here on the live feed. There you go. All right, so what you're looking at, we're looking at our sun here. You can just use your mouse to kind of move around. Sorry, it was a little fast. But you can determine which planets you can actually query this. So if you see in the bottom left, here's the 4,158 confirmed planets and about 3,000 star systems. If we zoom out, just kind of give you a sense of the footprint of all the planets that we're discovering. Let's zoom out to the galaxy here. All the planets that kind of look like in a cone off in one direction, those were actually mostly discovered by Kepler. The other planets that we discovered kind of around are from tests and other methods and other observatories. But if we kind of zoom out even more here, there's our galaxy. So again, all the planets that we're discovering are very close to home, kind of within our own galactic neighborhood, if you will. But feel free to click around in this. This is actually a really cool, useful tool. If you want to try to find a planet, like if you want to just look at just the discoveries made by the TESS spacecraft, you can click on that. And here's all the objects made by the TESS that was launched just 2 years ago. But let's say you want to try to find a planet itself. You can actually click on one. So these are all the confirmed planets. Like click on one and you can head right over there to it. And it gives you the star. It gives you the habitable zone. So this particular, I just clicked on a random one. For instance, this planet right here it looks like it's a gas giant. It will tell you kind of a little bit more about it, what we know about this planet by clicking on the info page here. You can see that it's roughly half the size of Jupiter. It gives you its orbital period and whatnot, and what it might look like. And if you can change your view by clicking on the system or the planet itself. And so you can actually see. Very cool to navigate around. But I'll leave you with that. So I hope you guys enjoyed it today. Hopefully I didn't go too long. Be sure to check in next week. We're going to be going back to our nighttime sky to looking at how the summer sky is starting to reveal itself. and we'll take a look at some of those morning planets again and some other sky happenings. So again, thank you very much. I hope you guys enjoy the rest of your weekend and have a happy Memorial Day weekend and clear skies. Have a good night.